I would like to expand our understanding of the double integral to include regions that aren't rectangles, to include general regions. I want to be able to integrate a function f of xy over this region, just like I would any other region. So in this video, we're going to redefine or define again the double integral, this time specifically with general regions, and we'll see another statement of Fubini's theorem that also includes this case. So what we need to do to start is to partition our region. So we kind of do the same thing we did before, where we divide it up into rectangles, but now some of our rectangles aren't going to be completely in our region. All right, so like I see this rectangle and the ones here, they include points both inside the region and out. I'm not gonna include those to start with. So right now, I only want to consider rectangles that lie completely inside the region. So I'm gonna shade those in very quickly in green. This one looks like it actually gets all of the points. It's real close though, but I'll include it and we'll just pretend if it missed a few points. So what I'm coloring here in green, just the points that are, just the rectangles that lie completely within the region are. And this is the partition I'll use. So now I do exactly the same thing I did before, where I take a sample point in each region. And I could get an approximation of this double integral by taking the sum of a function value evaluated at a point in each of those regions times an area. And then we'd think to ourselves, well, that would be an approximation. How do I make it better? Well, we're going to take a limit as n goes to infinity. And I claim that these things are equal, right? That this defines this double integral. And I know what you're worried about, right? You're worried that I didn't include the whole region. Well, what I want you to imagine is that right now, the green rectangles are kind of like a very blurry picture, a pixelated picture, right? It's like I took it with a very bad camera that doesn't have a lot of pixels in it. And so now as n goes to infinity, there are more and more little rectangles, which means my map gets finer, right? It has more little lines, right? So if I look in here, this would be divided up into a lot more little rectangles. And so I'd include more and more. It's like I could imagine drawing the region R now with finer and finer, smaller and smaller pixels, and eventually it would fill in all of the gaps and I would have all of the region R. So this is my definition of double integral. I partition my region with rectangles that lie on the inside of it, and as I let the rectangles get smaller and smaller, they finally do fill in all the missing places around the edge. Here is our stronger form of Fubini's theorem. I need a function that's continuous over a region R, and I need my region R to fit into one of two cases. I need to be able to model it with a top function and a bottom function, or a right function or a left function. So this here, G1 and G2 are functions on the variable x. Y is defined as a function of x. In this case, x is defined as a function on y. If R is defined in this way with a top function and a bottom function, I need my functions that bound the top and bottom to be continuous over the interval a, b. Then my double integral is equal to this iterated integral, where I bound in the x direction from a to b, and then the bottom function and top function become my bounds in the y direction. If I have a right function and a left function, I do the same thing, but now I'm going to integrate with respect to x first, right? My bounds are a left function and a right function, and then finally from c to d. In our next video, we're going to see an example where we get to use Fubini's theorem in its stronger form, but I want to go on and talk about how to find the bounds. And this is a process we'll write down and is printed in your textbook, but the idea is this. After we've picked an order of integration, right, and sometimes that'll just be by looking at it and saying, well, I can define this as a bottom function and a top function. What we do is we send a ray through the region parallel to the axis of first integration, right? So the direction of integration to start would be y. So I'd imagine sending a ray through in an increasing order of y. Well, first I would hit G1, I'd go through the region and I'd exit G2. That gives me those bounds. And then the bounds for x are the bounds that would contain every possible ray that would go through the region in that order. For the second case, where I have a left function and a right function, I do the same thing, but my variable of first integration is x. So I send a ray through the region. I hit the left function and then the right function. And then the bounds in the y direction are the bounds that would include every possible ray I could send through the region. So that will be our process for finding the bounds of integration and using Fubini's theorem in its stronger form.